Next, let's see the reference bit-based page access tracking mechanisms. Here we have again few other popular mechanisms such as Nimble and AMP research work. These research works, they improvise from the previous ones, right? In a way that performing the software page fault-based page access tracking is costly, as we see here from these reasons. It has its performance cost and its space cost. So not doing that makes sense if we do not need that. Do we need that? Well, we don't. That's why we have an alternate. That is by using just the reference bit, and somehow in order to take advantage of this reference bit based page access tracking, we would need to have the scanning mechanism that scans all the pages, and it's able to scan the reference bit of all the pages, and it has some notion of what to do with the scanned information. So in Nimble, it uses the existing page profiling technique of Linux kernel to exchange the top most recently accessed page in the lower tier with the bottom most pages in the upper tier. So what we are doing is basically finding important stuff from the lower tier and exchanging that with the least important stuff in the upper tier. That's a very basic but successful idea proposed in that work. It mainly focuses on, rather than identifying which page is more important than the other, the main focus of this work is towards improving the mechanism of performing this, implementing this thing itself. So things such as it improves the overall migration mechanism of existing Linux kernel, and it proposes things such as transparent huge page migration, multi-threaded concurrent migration, two-sided page exchange migration, etc. Finally, a work called AMP, it focuses on page selection mechanism based on popular cache replacement algorithms such as LRU, least recently used, LFU, least frequently used, and random selection. This work AMP is an excellent example of how information stored inside the reference bit could be used, but unfortunately, it is implemented on emulator. And there are, if you refer to the paper, you would get to know there are some challenges on running it into the real system because of the overhead that a real system would have in order to implement this least frequently used and least recently used algorithms. We'll see more details about how do we capture information of LFU and LRU. So as of now, after learning all these different mechanisms, we learned about how to use the persistent property of persistent memory by using different file systems. We learned about different modes that persistent memory allows us to access, that is either using memory mode or using the app direct mode. We learned about how persistent memory could still be used as a traditional block device or as a direct access device. And then we learned about if we for a moment, if we put the notion of taking advantage of persistence into our back pocket, then what are the options that we have in terms of designing a better memory tiering system with an idea of having the data spread it across multiple memories that we have available. And then depending upon the latency of access of those different memories, we want to store more important data in a more faster memory. So what are the gaps and what are the still standing research questions that you could think of as of now? First, identifying the hot and cold data in virtual memory management can cause high overhead. As we saw in both the previous mechanisms, which is either the page fault based mechanisms or reference bit based mechanisms, there is some overhead of identifying the importance of pages. How do we minimize this overhead? That's a key research challenge. For low overhead and efficient tracking, the Linux kernel implemented clock. This tracking of which page is important, that is also a key question applicable in caching mechanisms as well, right? Because there we would want to prefetch, or we would want to fetch the data that is more important into a faster caching tier. So traditionally, learning from the history, Linux kernel implemented clock algorithm, which is approximation of popular LRU cache replacement policy. Now, implementing LRU following its restrictions at its base, like implementing a pure LRU policy is going to cost more. So what is the next best thing to do? That's what the clock algorithm did. It's an approximation of an LRU with less overhead. So why don't we learn from history, right? If we can figure out to repurpose the clock algorithm now to help us in this new problem of tiered memory with different tiers and data being spread out across these different tiers, that would be good, right? Yes. As tracking access of every in-memory page is not feasible, LFU is considered impractical for virtual memory management. Do we have any, like clock is an approximation of LRU. If we have any approximation of LFU, then that may be a good techniques to use over here as well, right? Think of it, you can search of it yourself. Coming back to clock algorithm does not consider the frequency of access. So clock is just an approximation of LRU. So how do we, if we figure out a mechanism to somehow capture the details of the frequency into our clock algorithm, even that would be much more productive and useful, right? How do we do that? In tiered memory system, it is important to capture both recency and frequency for hot or cold page identification. So the standing research questions, two big standing research questions are how to identify hot pages for promotion based on recency and frequency. Second, how to design a simple and low overhead yet efficient system in the kernel. Do you have answers to these questions? Would you like to design such a system? Well, that's one of the research that we are currently working on in our lab, and we have some development to announce as a solution or our best working solution at this moment. We designed a system called multi-clock. In multi-clock, we are still using, we want to reuse as much, the whole idea is how can we reuse the concept of low overhead that is provided by the clock algorithm, but also capture frequency along with the recency that's captured by clock algorithm. That's what we call it multi-clock. So imagine that we have different tiers of memory, lower tier and higher tier. Higher tier is more faster, such as DRAM. Lower tier could be a slower memory tier, such as persistent memory. Now, in a traditional Linux system, we have active list and inactive list in DRAM. And we can have active list and inactive list similarly into persistent memory as well. The idea here is, what if we have another list, such as promote list over here. So when we are doing data movements, if we see that the data, every time we scan, we look at the reference bit. If we see that the data is accessed, then we promote it. Then we move it from inactive to active if it's accessed, if we notice that it's accessed once. If we again notice that the data in active list is accessed again, then we move it to promote list. So on and so forth, depending on how many lists we have in that level. And once we are at, let's say here, if we have one promote list, then if a data is further accessed, data residing in promote list is accessed, then we would want to move it to an upper tier, active list of an upper tier. So following the numbers over here, upon a new allocation, we could direct the new allocations. Sorry about that. We could direct new allocation to the DRAM if it's free. If DRAM is filled, then we can direct new allocations to the persistent memories inactive list. Once we are done with our allocations, now if DRAM is filled, then definitely we would have to kick some data out to make space for the new data. So that's shown by the number 2 demotion. Now for the data that's being accessed in the inactive list of DRAM, we would move that data to the active list of DRAM. For the data that's being accessed in the active list of DRAM, well, if that's the topmost tier, then that's good, because then we are accessing most of the data from the fastest tier that we have available in the system. If that's not the topmost tier, then we would move it. So then it would be a case something like for the lower tier over here. So then we would move that data to its upper tier. If the data is further finding, if we want to move some data from inactive to the active list, and if the active list is already filled, then we would have to make some space. So we would shrink and move some data from the bottom of the active list, thinking that this is arranged in the recency order. So recently used data is kept on the top versus bottom. Then we would move some data from the bottom to the bottom of an active list. That's how we would shrink. Then similarly, when the data inside the inactive list is used, we would move that to the active list in the lower tier as well. Now, when our inactive list of the lower tier is filled, what do? We do not have another list to shrink this data to, right? In that case, as what we show here by 6, we would have to swap or evict the data to another storage media. So in that case, we can no longer support storing this data inside the memory. We have the application is writing more data than what we could store inside memory, so we would be forced to evict. Either we would evict if this is the lowermost tier. If we have one more tier below this, then we would, same as what we are doing here, demotion in 2, we would just demote it to the inactive tier of its lower tier. Same as what we had 3 and 4, activate and shrink. We have 5 and 6, activate and shrink operations going between inactive and active list. Now, in traditional Linux mechanism, we do not have any way of interaction between these lists across different tiers. What mechanism like Nimble proposes is directly promote from the active list of the lower tier to the active list of the upper tier. But in that way, we are still not able to capture frequency. If we want to capture frequency, because top of this, exchanging the data that exists in the top of this bottom list with the bottom of this top list will allow us, because we know that this is more recently used data because it's sorted in that order. And this is less recently used data. It will allow us to organize the data, capturing the recency in some format. But we have no idea of frequency, how many times it is used. In order to capture frequency, a very simple but sweet idea is to add more lists. So every time if an item from this list is accessed, we would put that into the promote list. We could follow the same shrinking mechanism as before. But then depending upon these additional lists that we have, number of additional lists that we have, that much of frequency we would be able to capture. So now we can, with this such type of additional list, promote list, we can capture recency and frequency both. That's the core idea behind our research work, multi-clock. In summary, if we want to compare all these different memory tiering techniques under different axes of page access tracking, what page selection mechanism they use, are they NUMA aware, how much space overhead they make, what is the generality as is applicable to all types of pages or just the huge pages, how are they evaluated, usability limit of how practical it is to implement and deploy and use them, current compatibility, what open source kernel versions of Linux allow to support them, and what is the key insight behind these research work. If you want to have like a cumulative view of getting idea about all these metric for different works, then the static tiering, it doesn't do any page access tracking because it's static. It doesn't do any promotion or demotion. It's just not applicable. Yes, it is NUMA aware. It can be used directly with persistent memory, and it can be used with different kernel versions. There is not any key insight. It's very straightforward, right? Thermostat. The key insight behind the thermostat work is poisoning huge pages to collect the information from page faults. Again, you could see the comparisons across different metrics. Thermostat, auto-NUMA tiering, and auto tiering. These three are the technique that uses software page faults, while Nimble, AMP, and R work multi-clock. It is more inspired by scanning the reference bit and extracting the information from that. Different techniques uses different metric of recency or frequency or random for its promotion mechanism or its demotion mechanism. We see a variance there. Now, some of these techniques are NUMA aware, some of these techniques are not. In terms of space overhead, if these techniques have to maintain any additional counter, vector, bitmap, array, something like that, which most of the techniques inspired from page fault access tracking needs to, so they would have additional space overhead, versus some of the techniques could only be applied to huge pages, while most of the others could be applied to both 4K pages as well as the huge pages. Some of these techniques are evaluated by using real persistent memory DIMMs, while few others are just evaluated on emulator. Evaluating on emulator is an option, not bad, because we have very accurate persistent memory emulators, such as KVM, emulator designed on QEMU simulator. But if having an idea of deployment on a real system is always better over emulator, right? Because there are many system level caveats and many more things could go wrong when you are using a real system, which we might miss if we are using an emulator. Usability limits Some of these techniques, such as, for example, Nimble, it might require a specific launcher configuration setting. So for every application, the user of the application is responsible to set up or deploy the application using a specific launcher and configure its parameters. So it's an additional task, while nobody likes additional tasks, right? As less as possible, the best. So having no additional task is always the best. Each of these versions are tested using different Linux kernels. So we just have it for your reference over here. And again, the key insight of each of these research works is very interesting and novel. So that's why they are research works, where we have work like autonomous tiering. The key insight behind that work was NUMA balancing. Auto tiering, the key insight was to maintain an n-bit history for demotion. Optimization for huge page migration was key insight behind Nimble. Hybrid page selection is a key insight behind AMP. And key insight of one of our work is to capture recency and frequency both at a very low overhead. Now, let's look forward to what you can add to this table. If you can come up with a design of a more advanced tiering mechanism with your novel key insight that puts your idea apart from these existing ideas, that would be best, right? That brings us to the last thing of this lecture, which is revealing the discussion topic. So the discussion topic for this module is going to be, how can we further improve the memory tiering techniques? Can we use some of the on-par machine learning mechanisms to perform memory tiering in a better way? Discuss on that, think about that, and write your discussion post on this topic. That's it. That concludes our today's lecture. Thank you.